Okay, so we're happy to have Jaqueline for the third lecture. Please, Jaqueline, the floor is yours.
Thank you. So welcome back, everyone. I'm glad to see you all back here. So for our third lecture, just remembering that, well, we saw already some invariant measures. It's the biggest concept in ergodic theory. And then we saw the Poincaré recurrence theorem that shows us, okay, if you have a set that has positive measure, so infinitely many times the points are going to return to this set. So this is a way of obtaining information of your dynamics through measures, through invariant measures in this case. And today we are going to talk about ergodicity, define what's ergodic measures, and work a bit more on the examples. And in the last lecture, we will relate the concept of ergodicity that we'll do today with the concept given by Boltzmann that I talked in the first class, but I will recall later via the Birkhoff's ergodic theorem. So that's the plan. Okay, so recall what's an invariant measure, because this is the most important concept, as I said. Let's focus, I define also for flow, but today let's just talk of maps. So let's focus in discrete dynamics. You have a map that is measurable, and it means that you can measure all the pre-images of the sets, and an invariant measure is just a measure that gives the same probability to the same measure to the set and to its pre-image. So recall that we define like this because it's more suitable instead of using the image, no? Because pre-images are always belong to the measure space, to the sigma algebra, but not the images sometimes. So this is it's a more suitable definition. We already discussed this last week. So the nice thing is that we can guarantee that in a very general context, there is always at least one invariant measure. So you just need to ask for your map to be continuous and define it on a compact matrix space. So continuity plus compactness implies the existence of invariant measure. So you can start to work with invariant measure because most of your dynamical systems will admit an invariant measure. Okay, so a good property that we can, there are two ways of thinking. You have your map defined already, and then you want to know, well, there is an invariant measure related to it. That's what the theorem of existence of invariant measure says, yes, there is. But you could also have your map and have a measurer already that you want to, okay, I want to analyze my system with this measure, and you would like to check if this measure is invariant or not. And one way of doing this in an easier way is to not check for all the measurable sets, that the measure of the sets are equal to the measure of the pre-image, but you can just focus your attention on a smaller algebra. For instance, which is very nice, is that instead of check for all the Borel measurable sets in the line or in the interval 0, 1, you can only look for interval, for unions of intervals. Because it's an algebra that generates the Borel sigma algebra. So you don't need to check for all the measurable sets, you check for a smaller subset of measurable sets. All right, so continuing these examples that I started last week, I'll just recall we talked about the doubling map. Now the doubling map is simply the map that does double the x and takes modulus 1. So you can rewrite as 2x and 2x minus 1, and this is the graph of the map. And we saw that if we consider Lebesgue measure, it is the measures that more or less Lebesgue is the measure that gives the length of the interval. The measure of an interval is its length. Okay, so Lebesgue measure is invariant under the doubling map. So we already have an invariant measure for the doubling map. There is a natural extension of this doubling map. This is 2x modulus 1, but you can think of the decimal expansion, which you multiply x by 10, and you take the fractional part of it. So this is 10x minus the greater integer less than or equal to 10x. This is the fractional part of 10x. So this is the graph of the decimal expansion. And this also preserves the Lebesgue measure. Okay, we saw last week that the decimal expansion map is completely related to the expansion on how do I call it? To the expansion, the decimal expansion algorithm. You have a number, let's say between 0 and 1. You can express this as 0, comma, and some digits between 0 and 9. Okay, this is the decimal expansion. This is how we express the numbers. So this map, the decimal expansion map, is completely related to this algorithm. And we could last time extract some very pure number theory results using this map. So what's the idea? Your map is gonna serve like a model. This is the dynamical system modeling a problem. So this map, the decimal expansion, is modeling the problem of the algorithm of the decimal expansion. And using some properties via the invariant measures, we could obtain some results that are strictly number theoretical. So what we proved last time is the following. If you give me a number that the first digit after zeros, you have 0, comma, let me write. Let's say you have 0, comma, 7, and many other digits. We proved that almost every number that are like this, for Lebesgue, almost with respect to Lebesgue, almost every number have infinitely many sevens in this expansion. So we have infinitely many sevens. If it starts with the 7, we have infinitely many sevens, almost every point. Well, 7 was not special. We could start with other 0, 3, and then we will be infinite. You have infinitely many 3s on it. So another question that we'll treat later is that, well, what's the frequency that these 7 appear? We know that they are infinitely, but can you compare with the other digits? These appear more or less, they all appear equally. So these we will need for study this, we need Ergodic. So it's a way of transform your problem that is number theoretical to a problem of ergodic theory. That's what we did last time. Okay. So today we will study another example that is the continued fractions expansions. So the problem is the following. This is purely a number theory problem. So given a number, how can you find the best rational approximation of it? Now this problem has a solution, and the solution is called the continued fractions expansion. So let's see a bit of this algorithm. So what you do is the following. Start with a point that is between 0 and 1, a number between 0 and 1. And then you define A1 as the greater integer that's smaller or equal than 1 over x0. x0 is not 0, so you can divide by x0. And then you define x1 simply by taking 1 over x0 minus A1 that was defined. Well, notice that A1 is a natural number, and x1 can be 0, and it's between 0 and 1. If you write like this, then you can rewrite x0 as 1 over A1 plus x1. Well, it's simple, no? X1 is this guy. Then you pass x0 here. So you go up with x0, pass x1 dividing, and then you obtain this guy. X0 is 1 over A1 plus x1. Let's say that x1 that you obtain is not 0. If it's 0, that you stop the process that we are starting now here. X0 is going to be 1 over A1 plus x1. If it's different of 0, then you can repeat the same process. What do you do? You take A2 to be 1 over x1. again, the greatest integer that's smaller or equal than 1 over x1. And x2 is simply 1 over x1 minus a2. Again, you can write now x1 equals to 1 over a2 plus x2. And this implies that x0 is equal, well, x0 was 1 over a1 plus x1. And now you prove that x1 is 1 plus, oh, sorry, 1 over a2 plus x2. So then you obtain this conclusion, okay? So x0 is this number. If you find the xn equals to 0, you stop the process. Your process is going to be finite. If you don't find any xn that is 0, you can continue the same process by recurrence. So you define xn minus 1 to be a number between 0 and 1. That's going to be defined the following way. Okay, an is simply, again, the greatest integer smaller or equal than 1 over xn minus 1. Xn minus 1 is not 0, you can divide. Okay, xn is going to be 1 over xn minus 1 minus an. And then you write everything and you obtain that x0 is equally to this. Is this fraction, this huge fraction. That's beautiful, no? Okay. Then you can do the following. You define the following sequence. Zn is xn is the nth is the time that you are in the nth time of your process. So xn is here. The difference for Zn is that you stop on an. Okay, you don't consider xn, so you take this part of this. X0 is exactly equals to it, but if you don't take the xn, you are not in x0 yet. But if you stop in an, Zn is rational. So if you don't consider xn, what you have here is a rational number. You have to work a bit to prove, but it's simple because all the a's, an are natural. Okay. So moreover, you also have to work a bit to prove that Zn converges to x0 when goes to infinity. So this is what we call the continual fraction expansion. And the notation is like this. You call x0 is equal to this, and then you put the 3 dots to end to say that this x0 is the limit of the sequence Zn without these 3 dots. So the 3 dots is to say that is the limit. Okay, so it's the limit. This is the limit of Zn. And then goes to infinity. So that's a purely number theoretical algorithm, and says that, well, all the Zns, as I said, they are all rational, and you can prove that this is the best rational approximation that you can find. So in the sense that Zn is the closer rational, that closer to x0, such that any other rational with the denominator is smaller or equal than Zn, it's farther from x0 than Zn. Zn is the closer one. Okay. So just for fun, for instance, the continual fractions function of pi is, well, the 3, it's because we are considered only numbers between 0 and 1, but then you can add the integer that starts pi. We know that's 3 comma something, so that's the 3, and the rest are the an. So a1 would be 7. So if you want to write pi, you have 7, 15, 1, 292, 1, 1, 1, 1, 2, and so on. So that's the expansion of pi. Okay, that's not just for fun. You can play a bit with this algorithm later. Well, that's the point of view of number theory. So what we do, we introduce a map, we introduce a dynamical system to understand this problem. So that's the idea. Let's see if we can think of a dynamical system that can model this problem and obtain some information through these dynamics. Let's go back to our algorithm and notice the following. X1 is 1 over x0 x naught minus a1. A1 is the greater integer, smaller than equal than 1 over x0. So this is, we could write like this, x1 is equal 1 over x0 minus 1 over x0, this greater integer. And x2, it's 1 over x1 minus a2. So x2, it's 1 over x1 minus 1 over x1. But x1 was this. So what we are doing is the following. I started with x1, that was this guy, and then you do the same thing for x1. And then in the xn, you do the same thing for xn minus 1. So if you think a bit, this is a process of iteration. So the idea is to consider the map that takes 1 over x minus the biggest integer is smaller or equal than 1 over x, and start to iterate it. And this is going to give us the same process. Let's see it slowly. Okay. So we consider then the Gauss map. And the Gauss map is the map defined on the interval 0, 1. Simply by what I said, it's 1 over x minus the largest integer smaller or equal than 1 over x. Is the fractional part of 1 over x. Well, we cannot include the 0 because we are dividing by x, and then you put the image of 0 equals to 0 to define the whole interval. Okay? So it's not hard to make the graph, to draw the graph of this map, because you can realize the following property. Consider the intervals 1 over k. Ik. The Ik is the following interval. Let me pull a bit my notes of the graph space. I thought a lot with this graph to put it up, but LaTeX didn't want to help me, was not in a good mood with me. So the graph is down here, I don't know why. So I don't have much space and I wanted to write something. So here we have, I'll mark here for you, 1 over 2. I hope you can see, I'm sorry. 1 over 2. Then I'll mark here 1 over 3. And then it would be 1 over 4. Okay. The interval Ik is the interval, well, I1, for instance, it's half 1. The I2 is the 1 over 3, 1 over 2, and so on. No? So in the first one, look what happened. Inside of these intervals, the fractional part of 1 over x is actually k. So if you are in the first interval, a number between half and 1, the rational part of the fractional part of 1 over x has to be 2. So the rational part, the fractional part of 1 over x in this interval has to be 3, and so on. Okay. So what means that inside of these intervals, if I can mark here, inside of these intervals, the function of Gauss map is only 1 over x minus k. So in each of these intervals. So you have the map 1 over x, and you translate by k. It's just this. So it's not, if I'm not seeing so well, it's not a line. It's not a line. It's a bit curved. It's 1 over x, and then you translate it a bit. And this, when you get too close to 0, it has many branches, and then you cannot draw it so well. It appears that you have a strip, but it's there are too many branches too close. Okay, so that's the expression of the Gauss map. Then we can use the Gauss map to model the problem of continuous fractions expansions. So for each x0, we will define an by the following way. You consider an if the gn minus 1 of x0 belongs to the interval EIAN. So these intervals I, A, N is the intervals that I wrote here. I, K, it's 1 over K plus 1 over K. So it means that G, I, N minus 1 of X0 belongs to the interval, I'll write here, 1 over AN plus 1 over AN, okay? And then you just define Xn to be the Gn X0. Remember, X1 is 1 over X0 minus 1 over X0, the integer part. X2 is 1 over X1 minus 1 over X1 integer part. So this is actually G of X0. So X1 is G of X0. X2 is going to be G of X1, but X1 was already G of X0. So if X2 is G of X1, it means that it's G, X1 is G of X0. So X2 is the second iterate of X0. And so on. Xn is the nth iterate of X0. Okay. Well, again, if you have Xn that is 0, we stop the process. Because remember that we define G0 as 0. So if Xn is 0, stop the process. But this is, it's according to the algorithm, because if we had the Xn equals to 0 in the algorithm, we also stop the process. It means that the number that you start was rational already. If one of the Xn's are 0, it means that you start with a rational number. So your expansion is finite. If the number is not rational, the expansion is infinite. Okay. Of course, we are more interested in the infinite expansions because the closest rational to a rational is itself. All right. So the nice thing is that we have a measure here. We have a good measure that is invariant. We define it the following measure. The measure of each set, simply the integral on this set of C, it's any number, divided by 1 plus x dx. Well, if you know what's an absolutely continuous measure, it means that one measure is absolutely continuous with respect to the other one if they see the same 0 measures. So this measure is actually absolutely continuous with Lebesgue. So this measure will see the same 0 sets that Lebesgue will see. If there is a set that Lebesgue says this is 0, so this measure will also do the same. Okay, this is a good measure, it's invariant. And moreover, if we consider C equals to 1 over log 2, this is not a Kabbalistic number, you can compute it. But if you consider C equals to 1 over log 2, this is actually a probability. Recall that a probability is only that the whole space measures 1. Okay? So this is an invariant measure. Great. Once we have invariant measure, we can obtain some results. So the first result that we can think is the following. Let's take our favorite number, at least my favorite number again, 7. So the number 7 appears infinitely many times in the continuous fraction expansion of almost every number in the interval, for instance, 1 over 8 to 1 over 7. So if I fix this interval, 1 over 8, 1 over 7, the number 7 in almost every expansion will appear infinitely many times. Well, how do we prove it? How do we obtain this from the measure? First of all, this is an interval, and then you should prove that the measure of this interval, 1 over 8, 1 over 7, is positive. That's not hard to prove. This measure is positive. Great. If we have a set with positive measure, Poincaré tells us the following. For almost every point in this set, the points return infinitely many times. So for almost every point in this interval, 1 over 8, 1 over 7, we will have infinitely many iterates of G, the Gauss map, that belongs to this interval, 1 over 8, 1 over 7. Let me Sorry. I have to decide if you see the part of my lecture, or if I think I can move this to the other side. All right. Okay. So it's going to return infinitely many times to this interval. But if you are in this interval, it means that the AN is equal to 7. Because this interval is our interval. Remember, it actually this is the I7, is the interval 1 over 7 plus 1, 1 over 7. So this is the I7. AN is equal to 7. Well, if you are in this interval, you have AN equal to 7. One of the symbols, the first symbol, actually 1 is going to be 7. What does it mean that GN belongs to the interval? It means that AN is equal to 7. So if you belong to if the point X belongs to I7, then A1 is 7. If GNX belongs to the I7, so all the AN is 7. If you have infinitely many N such that GN belongs to this interval, so you have infinitely many AN is equals to 7. If you recall, who are the ANs? They are the numbers in the expansion. So these numbers will appear infinitely many times equals to 7. And these we just use the invariant measure and Poincare recurrency theorem. Okay, so let me erase these. Fine. So we only use it that it appears infinitely many AN is equals to 7, which is equivalent to say that GN belongs to this interval infinitely many times. Okay. Of course, again, like we did for the decimal expansion, 7 is just a number with a digit that we chose. We could have chosen another number. So it means that any number that we fix in a certain interval, it's going to appear infinitely many times in the expansion, in the fraction, continued fraction expansion. Well, another question is the following. Can we say what's the frequency that this number appears? Because I said, well, it appeared infinitely many times, but it appeared more than others. 7 is special, appeared more than others. And that if I fix 7 or I fix 3, 7 will appear more than the 3. How big is the frequency of appearance? Well, again, it's not special, and we'll see later that actually I think I'll leave it as an exercise because it's nice. But we'll see that we can prove using ergodicity that the frequency is actually 1 over log 2 log 64 over 63. Well, 1 over log 2 appears from the measure. We call that the C is 1 over log 2, but you can think a bit from where it appears the 64 over 63. Okay, recall that we are we are thinking of the, no, I cannot go back. We are thinking of this interval. Okay. Okay. So let's enter finally in ergodicity. From now on, I will consider probability spaces. Well, I told you that if you have a measure that is finite, so the measure of the set, let's say C, it's a positive number. You can always build another measure that is a probability. A probability is the measure that gives, let's say, mu, that gives to the whole space, I'm calling X, sorry, and the space is N. The measure of the whole space is C, different of 1. And then you can always build another measure mu, which is a probability. It is that the measure of the whole space is 1. How you do this? It's simple. Take a measure of, define the mu by taking the measure of A divided by the measure of the whole space. You normalize the measure, and that's now it's gonna measure the whole space is M. So the measure of M now is the measure of M over the measure of M, and that's 1. Fine. So you can always think that if finite or probability, it's the same thing. So we will fix probabilities, meaning that the measure of the whole space is 1. The whole class is going to be only probabilities. Fine. Then we consider a map that is measure preserving. Measure preserving, it's only another way of saying that the mu is invariant. Recall, if it's invariant, the measure of a set is equal to the measure of its preimage for all sets, all measurable sets. Fine. Now we'll define what's an invariant set. We know what's an invariant measure. An invariant measure gives the same measure for a set and for its preimage. That's an invariant measure for all the sets. Now I want to define an invariant set. An invariant set is a set that its preimage is equal itself. So the preimage of A is equal to A. Okay? Well, if F is invertible, then A is invariant if and only if the image is equal to A. So we define with the preimage because we can also consider maps that are not invertible. But if they are invertible, invariant means that the map does not change the set, takes the set to itself. Okay? Well, let's say you have an invertible. It's not hard to see, no? Because, well, you apply F into both sides, it's invertible. This is going to be A equals to FA. Okay, if it's invariant, you apply F and then you have A equals to FA. If you have A equals to FA, you apply F minus 1. And then you have A equals to F minus 1A. It's immediate. Fine. So why are you looking for invariant sets? Invariant sets are nice because I guess in my first lecture, I told you a dynamical system has to be defined from one space to itself because you want to iterate. That's your thing. That's what the thing that you do all the time. You iterate. You take a point and you start to apply it many times. You do Fnx. You want to understand the odds of points. So if the map does not act in the same space, then you cannot apply again and again. If you have an invariant set, you can restrict your dynamics to this set because the image of it is going to go to itself. So if you take F and restrict it to A, you can say that A goes to A because the image of A goes to A. So you can divide your dynamic completely. You get A here if it's invariant, and the complement. The complement of A is also invariant because if the image of A is A, the image of the complement cannot go to A. So the image of the complement is inside of the complement. So kind of divide in A and the complement of A. So study invariant sets. It's good because, okay, you have a big space. It's complicated to understand. Well, let's choose, let's see which are the invariant subsets. And then let's restrict the dynamics to each set. And then we start separated piece by piece. Fine. Okay, so an invariant set, for instance, that we know already, it's an orbit of a periodic point. If your map is invertible and you have a periodic point of period, let's say n, then the orbit of it is only x, fx to fn minus 1x. This set is invariant. What's going to happen is that when you apply f on it, it just moves the points. You have x, fx, and so on up to fn minus 1x. So if I apply f, this goes to this point, you just mix this point like this. The points like this, and this goes here. The set just rotates. Applying the map on A just rotates the order of your points in the set, but that's it. It doesn't change anything. So this is an example of invariant set. So orbit of periodic points. Okay, so finally, what's an ergodic measure? an ergodic, you start with a measure preserving transformation. It is the map. It's defined on a probability space already. You have a measure already, and this measure is invariant. This measure is already invariant. Okay, it will be ergodic. So ergodic, it's invariant plus something. So to start to be ergodic has to be invariant. Many times we write invariant and ergodic together. So it has to be invariant to start with. And then to be ergodic means that all the invariant sets are trivial. Trivial in the point of view of the measure. What does it mean? If you have an invariant set, the measure of this set is either 0 or it's 1. Meaning that, well, your invariant set is either nothing, it's an empty set, or it's a whole space in the point of view of the measure. So if you have an invariant set, a priori, you could divide your dynamics in the invariant set and in the complement of it. What ergodicity says the following: you cannot divide your dynamics. You cannot decompose your dynamics, because if you have an invariant set, it's either already everything, the measure is 1, or it's nothing. We can ignore it, the measure is 0. So I'm going to talk more about this, but the ergodicity it's a concept of, I will not be able to say this word, indecomposability. You cannot decompose. It's a concept that guarantees that you cannot decompose your dynamics. Okay, so we can think that the ergodic measures are actually like the prime numbers. For the ergodic measures for measures are the prime numbers for numbers. Like the relation is this. This is not an analogy that I did. It's I think it's due to Corina Utigrai. I like it a lot. I haven't seen another place comparing the ergodic measure with the prime numbers, but I thought that's a very good analogy, and then I will tell you more later. Okay, so let's think why they are the primes. Well, consider a set that is invariant and it has positive measure. So it means that the measure is not ergodic. Take mu, no ergodic. Okay? Because if it's ergodic, this cannot happen. If it's ergodic, the measure of an invariant set, it's invariant. It's 0 or 1. Okay? Other sets can have measure of anything. Note that the ergodicity talks only about the measure of invariant sets. You can have other sets that has measure half, measure 1/3, one measure, I don't know, p/4. Can have any number between 0 and 1. But we are talking about invariant sets. Fine. So suppose you have a measure that is non-ergodic. It means that there is a set invariant that has positive measure. Okay. Then we can decompose this measure into two invariant measures. One I will call mu A, and the other one I will call mu M complement A. Well, and then we could analyze the measure, the dynamics F restrict to A and F restrict to M, to the complement of A using these measures. So the idea is that if you have a measure that is non-ergodic, you can completely decompose your dynamics in two subsets and have two different invariant measures and singular with each other to study this set. Let me give you an idea how we could do it. Okay, you have your space, and let's say that you have here a set A that has positive measure. So this is the set that has positive measure. Mu is not ergodic. Mu is non-ergodic. Okay. So you could define a measure mu depending on A by the following way. Well, for each B that's measurable, you could just do the following. Let's take a B inside of M that is measurable. This is M and this is B. You could measure only the piece that intersects A. So let B has this whole set, but I want to give, well, I just want what is being seen by A, what's inside of A. By this, I can define the following way. Well, do the measure that you start, B intersection to A, and divide by the measure of A. Because in this way, you see the relative measure of B inside of A. Because if you just do the measure of B intersection to A, this is not going to be a probability. But then you divide by the measure of A. Notice that you can divide because the measure of A is not zero, it's positive. So that's important. That's why when you use the hypothesis. So you can divide by it, and it's not hard to prove that if mu it's invariant, mu A is also invariant, and it's a probability, it's an invariant probability. On M, define B belongs to M, it's a set inside of M. So it's an invariant probability on M. You can also define the mu in the complement of A, more or less in the same way. You do the measure of B intersection to the complement of A, then you see the rest. You had, now you measure this part that is in the complement of A, but then you divide by the measure of the complement of A. Well, if the measure of A is positive and is not 1 also, because we are supposing that the measure of A, we are in the case that's not ergodic, so the measure of A is between 0 and 1, the measure of the complement of A also have to be between 0 and 1. Well, if the measure of A, the complement of A is 1, the measure of A should be 0. Because if the complement of A is everything, A is nothing. What's left, the complement is 0. Okay, if the measure of A is 0, then the measure of the complement has to be everything. So there is no way. If the measure of a set is between 0 and 1, the measure of its complement is also between 0 and 1. So then you can also divide by the measure of the complement. And this, now you have the relative measure of B inside of the complement of A. So these are also invariant probabilities. So now you have 2 invariant probabilities, and you could study F restrict to A with mu A, and F restrict to M minus A. A is invariant, no? So then F restrict to A goes to A, and F restrict to the complement of A also goes to the complement of A. So then you have 2 dynamics. You divide your dynamics in this set red, A, and the outside of A, which is complement. Well, so in general, what we have is this, that non-ergodic invariant measures, they are decomposable, and ergodic measures are indecomposable, or something similar to it. It's good that I wrote. So that's a very important property. The ergodic measures cannot. So in this sense, you think about the primes. The primes are the numbers that cannot be divided by others, except for itself or 1. So the ergodic measures are the measures that cannot be decomposed by other invariant measures. Okay, and there is a very nice theorem that I will not have time to speak about, but I will just give you a few words now. That is the ergodic decomposition theorem. If you have an invariant measure, for each invariant measure, you can decompose it in a way with all the elements in the decomposition, they are ergodic measures. So you can always write in a, it's not going to be always finite, but you can always decompose any invariant measure in ergodic measures. So in this sense, the ergodic measures are really the block that builds the whole invariant measures. So they are the smallest one, they cannot be decomposed. You cannot divide them in pieces of invariant measures. And for write any invariant measure, you can also write using ergodic measures. So this is a very good analogy with primes, because indeed that like the ergodic measures are for the invariant measures, what the prime numbers are for the integer numbers. It's a good analogy for you. Again, it's a nice analogy that I believe was done by Corina Utigrai. Okay.
Sorry, Jaqueline, may I question real quick? It's like regarding this decomposition, is it also unique up to, I don't know, some sort of invariant function, you know, that's gonna make something?
The composition theorem, yeah.
It guarantees uniqueness as well.
Yes, you have a family of ergodic measures. It may not be finite, but it's unique. Yeah, it's a nice theorem.
That makes sense. Thanks.
Okay.
Can I have asked
the
one
analogy
question?
is really good, no? Sorry, Asad, can you say, please?
Yes. My question is that, so there are two different definitions, they're different concepts, invariant measures, so ergodic. So we can define in different way. I mean, it's not necessarily to define ergodicity with the invariant. In many systems, they have ergodic measure, but not invariant. So, and many system has invariant measure. So, but you use together here. The other, can you clear me something about this confusion? The other question is, okay, if it's not ergodic and then you decompose into subsystem, so what's the disadvantage of this system when we decompose into two systems? We can study, it's good maybe. If it's not good, can you tell me something about that? So I'm
when
going to
decompose in the two systems, it can be good. Sometimes you do this. It's I'll answer backwards. So the decomposition in two systems can be good, but when you have the property of ergodicity, it's a stronger. When you decompose into systems, basically you have two dynamics. It basically says that, well, you could have written in another way, instead of using this map to map the dynamics, you could write two maps, basically this. So they are not related. It's like, okay, you have, for instance, you could think think it's a trajectories of some flow, and then you have a trajectory that goes here, that are entering all. If you have this in this part, all the trajectories here are entering and converge to this point inside, and here in the other side, I don't know, you have like a bow and eye that does everything is doing like a butterfly around these 2 points. So these two parts have no relation. So that it's not really interesting as a whole system. It's important to understand that sometimes we understand the dynamics by taking pieces, but they are not related. To be related, the points should be walking around, going to both sides. So to a dynamics to be very interesting, we should have a positive entropy. It's another concept in ergodic theory that I didn't define, but it means that the system is very mixed. The points are passing everywhere. So this is a good thing. If you are completely separate, you basically have two dynamics different. So it doesn't have this kind of good dynamics in the sense that you have the whole space is it's missing my word. It's missing the word. You have connection between the points in the whole space. The points are not stopping in a side of the space. It's like, okay, you divide it completely. If you have A and the complement of A, the points are not passing between one side to another. You put a wall, and that's not so interesting as dynamically speaking. But again, you can use to study, because there are systems that are like this, and then you study them. For the other question about invariant measures, ergodic measures, in the next class, I will define using the averages. And that's what you meant. That you can define ergodicity through the averaging. in the new point of view of ergodic theory, in the classical ones, at least from the books that I know, from the more modern, not classic, modern point of view of ergodicity, we always consider that is invariant. But in other fields that recall the physics definition, you may just think about ergodicity not through invariant measures, but through the averages of observables. And that we'll see the next class. So in the next class, I will answer your question better. Okay, so yeah, there is this other definition, but for the dynamical systems, the definition is also with invariant measure. We will see that the definition with averages are equivalent, but we consider always that a ergodic measure is to start with invariant in dynamical system. Okay.
Okay.
But,
okay. Thank you.
I think it answered more or less, no? But we'll see it with
Yes.
carefully
Yes. I understand.
with
Okay.
the ergodic beef of theorem next time.
Okay.
Okay.
Thank you.
You're welcome. Okay, so the ergodic measures are the bricks of the measure, and we can also see as extremal points of some convex set. So we can think about number theoretic ideas that we cannot decompose the measure, and now we can also think of more algebraic or geometric way. So if you let's say that you gave me two invariant probability measures, and then you do the linear combination of each. P is just a number between 0 and 1. So you did the linear combination of it, and you create a new probability measure. This is also invariant. It's not hard to see that if you define the measure in this way, if mu1 and mu2 are invariants, the mu will also be invariant. So what did you prove with this very simple comment is that the set of all invariant probability measures is convex, because convexity means that every time you have 2 points in a space, the linear combination, it also belongs to the space. So if you have 2 invariant probability measures, you do the linear combination, this is also an invariant. So it belongs to the invariant probability measure space. So this is a convex. Well, what we can prove is that the ergodic measures are the extremal of this convex set. Recall that an extremal of a convex set is the set that if when you are in a convex set, you take 2 points in this set and you do the combination, it means that you are taking a line that contains these 2 points. The whole line has to be inside of the set. But the extremal, sorry, not the line, a segment. You have 2 points and then you do the segment that connects these 2 points. The whole segment belongs to the set. Extremal in a convex set is the points that are in the extreme, in the sense that they are not combination of the others. So you cannot write them as a strictly linear combination. You cannot consider T between 0 and 1. If mu is an extremal, it has to be 1, or it's equal to mu2, or it's equal to mu1. You cannot combine them. So a measure is ergodic if and only if it's an extremal of the probability measures, invariant probability measures set. So it means that you could maybe, okay, we've been seeing that you have many applications in number theory. You study ergodic theory, you have many applications, and you have even more powerful application, as I told, for instance, the Green-Tau theorem. That's really, really incredible. So we just saw some small applications, but we have many applications of number theory. You can also start to think that, well, we also use functional analysis for proving stuff. So to prove the existence of invariant measures, you use the weak star topology. So use tools of analytical tools. But you could also start to use other tools. If you think of the ergodic measure as the extremal of the convex set, then you could maybe use some more algebraic geometrical approach and start to understand these points. So this is also a line in ergodic theory. The beauty of ergodic theory, one of the beauty I think is this, like it's a probabilistic point of view. We are including measure. It's based on a measure theory, okay? It's a dynamical system idea. You have to study the dynamics, but you need to use tools of function analysis or other analysis. You have to use analytical tools, but you could also go to other paths. Maybe let's take a point of view more algebraic. So this is really a world that you could travel for many different directions and do research in many different directions. This is just our first date with ergodic theory, let's say this, but can be a long life relationship with ergodic theory, and you can travel a lot. Well, on time that we cannot travel, and you should not travel, it's good to be able to travel at least inside of ergodic theory. Yeah. So given this propaganda, let's see some examples. I think I have more 10 minutes. Yes. Okay. So let's see this nice example that are the circle rotations. You have a rotation of the angle alpha. You can think, well, you can think of the circle as the R quotient by Z, for instance, and you write in this notation of sum. So it's X plus alpha, but what you are doing is the clockwise rotation by 2 pi alpha. So you have your circle. Let's see if I can do a drawing. You have your circle, and then you rotate it, choose a point, and then you rotate of the angle 2 pi alpha. All right. So we have some dynamics information of it. It's not so hard to see, but the first one at least. If you have if you choose the angle, this is a family of maps. For each alpha, you have a different map. So if you choose the alpha to be rational, then all the points are periodic, because you are rotating off a rational angle, let's say P over Q. If you do it too many times, you go back. So you have your circle. Let's say you rotate over P over Q is half. Then you do you rotate P over 2. Then you come here, and then you rotate P over 2 again, and then again. Oops. And then you come back here. I don't know. It doesn't want that I write. Okay, so all the points are periodic. They return, the odds are going to be, all of them are finite. It's a very simple dynamics if alpha is rational. But if alpha is irrational, then it's completely opposite. So then all the odds are dense. It means that if you write the odd of a point, we call it X, A alpha X, and so on, and alpha X. So this set, the closure of it is the whole circle. So it's gonna start to iterate, it's never close because it's irrational. So you can rotate, you are just rotating clockwise your circle. So you rotate, the points are never close, the odds. So the odd is, each point has the odd dense. So it's completely different, because when alpha is rational, you have finite finite odds. All the odds are finite. You know completely the dynamics. Remember that our goal in life is to discover the odds, to understand the odds of a point. Well, here we understand completely. All the points are periodic and all the points are dense, depending on being rational or irrational. So this map is completely defined by an algebraic property of the alpha. Okay, so then let's introduce some measures to make it more interesting. So let's consider Lebesgue on the circle. Remember that Lebesgue on the line is just the length of the interval. Lebesgue on the circle, you can think that your circle is the following. You have the circle. I was proud to be circled so beautiful with the tool, and now it was horrible. So you can think of the interval 0, 1, and you can think that your circle is just identifying 1 with 0. You glue these 2 points, and then you make a circle, okay? So you could think of the length of the interval, but then you glue it again. So then you define like this. Lebesgue measure on the circle is simple. The length of the arc, you choose an arc. It's gonna be the length of the arc divided by 2 pi. Because the arc is gonna be 2 pi something, and you want to be a probability, has to be between 0 and 1. So divide by 2 pi. Okay, so generically it's just the length of the arc. So it's the length of the arc. Fine. Well, note that we want to prove that Lebesgue is invariant. Okay, Lebesgue is invariant. To prove that it's invariant, we have to prove this. We have to prove that for all the arcs, the of the rotation is equal, the measure of the preimage of the rotation is equal to the measure of the set. But the preimage of a rotation, it's another rotation. You think you rotate here, the preimage is going to be just rotate counterclockwise. You are rotating clockwise, and the preimage is going to be the negative rotation, which is basically, not basically, which is really the counterclockwise rotation. So the preimage is another rotation. But anyway, what a rotation does with the length of an arc? You have an arc, you rotate it. The length of this arc is going to be the same. You don't change the length of the arc by rotating a circle. Take the circle, choose an arc on it, have this circle, choose an arc. Rotate it of some angle. Okay, it's going to appear here. This has the same, well, this doesn't have the same length because I didn't draw it nicely, but let's adjust, and then, okay, these have the same length now, these two. So rotate's not going to change the length. So the length is the same, so the Lebesgue measure is the same. So this is it's indeed an invariant measure. So Lebesgue are invariant for any rotation, and I didn't do any difference between being rational or irrational. For any rotation, Lebesgue is invariant. Okay, now let's show that actually for rational rotations, these are not ergodic. Lebesgue measure is not ergodic for rational rotation. If alpha is rational, let's say that's P over Q, and P and Q are co-primes. It means that when you divide between themselves, the division, they don't divide one each other, okay? They are co-primes. So you consider the rotation, Lebesgue is not going to be invariant. Ergodic, sorry. It's not going to be ergodic. Well, recall that to be ergodic means that any invariant set either has measure 0 or measure 1. That's ergodicity. Measure 0 or measure 1 for each invariant set. Then, if I want to prove that it's not ergodic, it's enough to build a set which is invariant. So it's important that the set is invariant. It's necessary now that the set is invariant, and has measure different of 0 or 1. It's measured between 0 and 1. Some positive measure that's not 1. Okay, so that's enough to prove that is not ergodic. So to prove that Lebesgue is not ergodic for the rotation, for the rational rotation, I will have to build an invariant set with a positive measure that is not 1. So the set that I would do is the following. You consider A, this set. This is a union of arcs. I'll try to do a draw, and this works for each Q. The Q is fixed there. P over Q is fixed. Is the angle that I am rotating. So the rotation is R alpha, which is RP over Q. So this is Q here. But let's say that I chose Q equals to 4, just to see this example. Then you do the circle. Then I'll do the following. I'll divide my circle in 4. Okay, in 4 arcs. I have 4 arcs. And what are these? What is this set if Q is equals to 4? This set is the union of, well, the first one is going to be 0 over Q, so it's 0, to 0 over Q plus 1 over 2 Q, so it's 0, 1, 8, union with 1 over 4, 1 over 4, Q is 4, 1 over 4 plus 1 over 2 times 4, 1 over 8. So it's 1 over 4 plus 1 over 8, but 1 over 4 is 2 over 8. So this is 3 over 8. This is 2 over 8. And then so on. What we have is 4 arcs that are the following. The first one, let's say 0 to 1 over 8. So the length of it is 1 over 8. The next one is 1 over 8, 2 over 8 to 3 over 8. So it's the half of the length of, I divided in 4. So it's the half of each part of 4. And the next is here. And the last one is here. So the set A is the union of these 4 arcs in black. That's my set A. For Q, if Q was equal to 8, to 4. If Q is not equal to 4, and then you always have Q arcs, but with the length of 1 over 2, the length of the arcs that I define, we'll have Q arcs, the union of Q arcs with the length is, if you do the computation, it's 1 over 2 Q. Okay, in our case, it's 1 over 8. Fine. So what is the measure of this set? First of all, is this set invariant? What means invariant? In this case, it's invertible map. So is this set invariant? Well, to be invariant, the image of this set should be itself. But please, no, because what the rotation P over Q do is the following. It does the following. It takes the arc and passes to the next. The image of the first arc is this. The image of the second is the third one. The image of the third one is the fourth one, and the fourth one goes back to the first. So it just rotates your circle because you define exactly the size to be 1 over 2 Q. So that's not hard to see that it rotates, and it just rotates like this. So the image of the set A is actually the A. The only difference is that you move a bit. The first one goes to the second goes to the third, and so on. Fine, this is an invariant set. It's invariant, so then A is invariant. A is invariant. What do I need to prove? I need to prove that the image by Lebesgue of A is between 0 and 1. Well, the image of Lebesgue, the measure by Lebesgue of this set, let's do the computation for Q. What is the length of A divided by 2 pi. Well, the length of A actually is the following. The first one is 1 over 8, the second one over 8. Each one is 1 over 8, but you have 4 intervals, and they are all disjoint. Then you can do the measure of the sum. So it's 1 over 8 times 4. So this is 1 over 2. In general, for A, that's the way that I wrote, it's just you have Q intervals, and each one, the length is 1 over 2 over Q. So actually, the measure of this set A is always 1 over 2. So it's always half. And it's always positive and not 1. So you build a set that is invariant and has positive measure. So this is impossible to be ergodic. Then we prove that the rational rotations are not ergodic. Okay, so this is just the generalization that I just did. Well, irrational rotations are ergodic. And that's when we see the difference of the dynamics could have been seen, because for invariant measures, we didn't see the difference. We showed that, well, all the Lebesgue is invariant for all the rotations. but the rotations are quite difficult, quite different. One rotation, when alpha is rational, has all periodic points, and the other rotation, when alpha is irrational, has only points with dense order. So the dynamics, it's completely different, and the measure should see it. Lebesgue should see it. If Lebesgue is not seeing it, it's a problem. Well, it don't see when you consider only invariant measures, but when you think about the properties stronger, like ergodicity, then you show completely difference. Irrational rotations are not ergodic, but irrational rotations are ergodic. I think this is a good topic for include maybe in the of a suggestion for a student's presentation. This is very nice. There are different proofs, and there is a nice proof using Fourier series that I think who have studied already. At least I know that Lamartine studied. I'm doing bullying with my students. I know that Lamartine studied Fourier series, for instance, but who studied Fourier series could do, and he also studied rotation. So it's a big bit of a bully. Sorry. I like all my students. I'm not so mean as it appears. But that's a very nice topic, I think, for the students to present. I also have other suggestions in this thing, because actually all the other examples that we saw are ergodic. So the doubling map is ergodic, the decimal expansion is ergodic, all related to the Lebesgue measure. No? Lebesgue measure is ergodic for all the examples that we saw. So this could also be included as presentations. They are simple and nice, and can use two different points of view. You can use, if you don't see the Fourier series, you could, but you study measure theory, you could use the disintegration Lebesgue theorem to prove it. So it can even use maybe both. That's a suggestion for Stefanella too, because some of the students have to present something. Okay, another last suggestion that I didn't present, but it's nice, is the shifts. The Bernoulli shifts are very nice example. So it could be done, the presentation more detailed of the model, and then also prove that the measure that you define there, the Bernoulli measure, it's ergodic. Okay, so just to finish, I'll give some scenes of the next episode of our last lecture. So recall that the decimal expansion now is the fractional part of the 10 times x, and well, I didn't prove, but I'm saying that ergodic Lebesgue measure is ergodic under the decimal expansion. It is going to be work for the students. And let's define what's a balanced number. A balanced number, it's a number that every digit appears with the same frequency. You have the decimal expansion of a number, and a number it's called balanced if each digit appeared with the same frequency 1/10. You have 0 to 9, then it has to be, if everyone has the same frequency, it has to be 1/10. Okay. Well, it's not hard to think of a balanced number. Think quickly. Construct a balanced number. Well, 0.123, 9, and then repeat 0, 1, 2, 3, 4, 9, and then repeat this block. Take the block between 0 and 9 and put after the comma, and then repeat this. If you create a number that is balanced. So it's not hard to create balanced numbers. It's hard to decide, given an irrational number, to decide if it's balanced or not. For instance, we do not know if pi is balanced. We do not know if every digit on the decimal expansion of pi appear with the same frequency. Well, we still don't know this. Maybe you can work on it in the future, but we at least know that almost every number is balanced. It means that the Lebesgue measure of the set of the numbers that are not balanced is 0. So the Lebesgue set of the measure the Lebesgue measure of the set of the balanced numbers is 1. So the complement of the set that the balanced numbers has zero measure with respect to Lebesgue. So for proving this, we use the Ergodic-Birkhoff's theorem, and we will relate the time that the point is spent in the set. We relate this with ergodicity. So that's related to the question that Assad did with the different definitions of ergodicity. I thought a lot of first defining in this way of averaging, and many books actually do like this. They start with Birkhoff's theorem, and they do the concept of ergodicity much later. But we have an ergodic theory course, mini course, and to leave to define ergodicity in the last class is a bit depressing. So I thought that it's better to introduce the definition before doing the Birkhoff's theorem. So, but most of the books you see, like it starts ergodicity in the 5th chapter or in the 6th chapter. You do a lot of ergodic theory before you start. You see the definition, but well, so I thought that this was a better deal. But in the next lecture, in the last lecture, I will indeed relate these two concepts via the Birkhoff-Ergod's theorem, which is a very beautiful theorem. And well, that's it for today. So thank you.
Very good. So let's thank Jaqueline. So there's that.
Thank you so much.
Question? No question? Everything was very clear, Jaqueline.
Yeah, I think also I scared a bit everyone.
No, I'm sure that everything was clear. Let me see. Let's see if there are questions here. YouTube.
So let me just add, as I said, I'm doing I'm trying to do a big advertisement for ergodic theory. Now it's my field of research, and I really enjoy it. I find that the first time I studied ergodic theory, I decided, well, that's it. I was in the master's and I did the ergodic theory course, and I told my advisor that that's it. That's what I want to work with, and it's very nice. And as I said, you have many paths that you can take, and in time you get as a researcher. For the youngers, it may appear hard to think about this, but in time, as a researcher, you get a bit tired of some things. You change a bit of your taste. And in ergodic theory, you have the possibility of change also the point of view, move towards other fields and do more applied things. And right now, for instance, I also have a project with a bit more of applications, and or you can go for more topological things. It's a very nice way. Another thing that I would like to say is that it's important is that I did this course with a few applications in number theory. I have to do a confession that when I was a student, I could not stand the applications of number theory in ergodic theory. I definitely didn't like it. In time, I learned to appreciate, and now I really like some of the applications, and maybe in a few years I'll go back to dislike it again and change. But this, I can see now, right now, the beauty of it. But if maybe like me, a few years back, you didn't like much the applications in number theory, let me just say that that's what I did for this mini course, trying to reach most of the students that may not have much background. This is not what we really need to do in ergodic theory. You can work in ergodic theory without having to work with a number theory applications. So I don't want to pass the wrong idea that this is what we do in ergodic theory. It's not. So for instance, I don't work with applications in number theory. But for a first mini course, for the first date with Ergodic theory, I think it's a good advertisement. And then in more time studying more, you can do other things. So just let me not give you the wrong idea of it. Okay, so if anyone has questions, comments, complaints?
No, complaints, I'm sure not. No question?
We have only appreciation. So I think it was very nice lecture. You explained everything very well. So yes, it's very helpful for us. Thank you so much.
Okay, thank you. Thank you.
So, okay, I think also in the YouTube, no questions. So we can close for today. So we will see each other in 2 days for the last lecture. And next lecture, we collect the list of people that need a certificate, you know, because for each mini course, people might need a certificate, so we can send you the certificate, okay? If I forget, remind me, because I'm forget. Okay, so remind me.
Okay, I'll try.
Okay.
The young people should remind us.
Yeah, so we'll have a circulating. Okay. So thank you to everyone to be here, and see you on Thursday.
Okay, so see you all on Thursday.
Bye bye.
Bye bye. Thank you.
Bye bye. Thank you, Jaqueline. Bye bye.